Royal Caribbean's Oasis-class cruise ships. Maritime engineering at an unprecedented scale. Since 2009, they've held the title as the largest class of passenger ships on the planet. And today, a third Oasis-class vessel is under construction. The biggest one yet. Longer, wider, and heavier than any other that's come before it.
The amount of technology, engineering, and design that has been put into this ship class is quite extraordinary. It's simply mind-boggling. Nothing like the Oasis class of ships has been built before. This is in a class of its own. The complexity of it is really staggering.
Sitting next to her makes me feel like standing next to a skyscraper.
When it's finished, the Harmony of the Seas will be almost 8 times longer than the Statue of Liberty is high, and 2 times heavier than the world's largest aircraft carrier.
It's about 360 meters long. The funnel is reaching a height of 65 meters from the water level, and her gross tonnage is 227,000 tons. She is the largest ship ever built.
Building a ship this big would be impossible without some guidance from the engineers of the past. Boats have fascinated humans for thousands of years.
Thank you.
The ancient Egyptians built vessels from reeds. They were perfect for cruising the Nile. But their absorbent nature meant they didn't last.
Wood.
For centuries, wood was the boat-building material of choice. Warfare led to the use of metals like iron. But iron is brittle and prone to rust. A new material was on the horizon. Steel, and it would go on to revolutionize the world.
In the chamber behind me, there's about 150 tons of liquid molten steel. The temperature is phenomenal. It's about 1,650 degrees Celsius.
Steel is made by mixing iron with various metals and elements.
The crucial starting point of the steel-making process is to remove the carbon and the other impurities. And now it's being poured into the ladle, and it'll go to the next stage, which is to take it to the converter.
The steel is modified by adding extra alloys and blowing in oxygen.
What's going on here is the very basics of steel-making. And this wouldn't have been possible today without the pioneering work of one engineer that's known throughout the world by all material scientists.
For centuries, steel making was an incredibly difficult and lengthy process. That was until the 1800s, when inventor Henry Bessemer came up with a solution.
Traditionally, the wrought iron was layered with charcoal and heated over days, and the charcoal would diffuse into the iron, and that would produce the steel qualities. Very complex and difficult to achieve, and therefore very expensive historically.
Bessemer developed a way to mass-produce steel.
And this is it, the Bessemer converter. It's a huge, vast, cylindrical chamber, about 6 meters high, and it would have held 25 tons of steel.
The converter's capacity is impressive, but its real ingenuity is in how fast it creates steel. Bessemer discovered that pumping air into iron accelerates combustion, increasing carbon reduction and burning off impurities, resulting in quality steel in a fraction of the time.
to show how oxygen injection really increases the combustion process, I've got a simple demonstration here. I've got a tray of charcoal. With my thermal camera, I can see the temperature of these coals at the moment. It's around about 450 degrees C. So now what I'm going to do is start to blow pure oxygen onto these coals and see the effect. Wow, look at that. The impact is amazingly impressive. So if I now look at the temperature, it's gone up to 1,000 degrees C, a hugely dramatic increase in the temperature of these coals. So Bessemer had found a really amazing process to reduce the carbon in steel.
Mass production of steel took off. Its elasticity and strength made it a hot commodity for railroad and shipbuilders.
And although processes have become more sophisticated and complex, it was thanks to the engineering genius of Sir Henry Bessemer and his revolutionary machine that over 1.5 billion tons of steel are now produced annually right across the globe.
The Harmony of the Seas needs a staggering amount of steel. When finished, the ship will be longer than 5 football fields back to back and weigh over 227,000 tons.
Harmony of the Seas requires approximately 50,000 tons of steel.
Massive steel sheets are delivered to the assembly plant by train. Automated systems cut the sheets into thousands of individual components.
Here we have one of the pieces. This is normal strength steel, a very typical piece. Thousands and thousands of pieces like this on board.
The steel panels, girders, and smaller components are welded into modular sections called blocks.
After the panels have been fitted with stiffeners, we start erecting the bulkheads onto the panel. And at this stage, we start calling it actually a block. This is typically a 1-deck high block of steel which has the deck, the bulkheads, the pillars, everything it needs to form one deck of the ship. The block, as you can see now, it's turned upside down. So actually we're looking at the ceiling of any given deck. And the reason why it's like this is, of course, that it's much easier to weld everything when it's in this position instead of welding in the ceiling. And once the outfitting is mostly completed, then it's turned upside down, or the right way actually, and then you start building blocks on top of that.
Individual sections are joined together, forming what are called grand blocks. There are 90 grand blocks on the Harmony of the Seas.
Here we have one of the grand blocks, one of the 90 grand blocks. And this is actually consisting of 5 decks. It's one of the highest grand blocks we have. So for this, you need probably around 10 blocks to make this one big grand block.
A custom-built gantry crane lifts each grand block into the dry dock.
A grand block, when the crane lifted it up, it can weigh up to 1,100, 1,200 tons. And that is, of course, quite a massive load.
The 90 blocks come together to form the world's largest passenger ship.
It actually could be compared, and this is, of course, simplifying it a lot, but you can compare it to building a Lego structure, actually.
But how do such gargantuan structures move across the open ocean?
The engines are the heart of the ship. Without the engine, the ship is not alive.
Designing an engine for the Harmony of the Seas will be impossible without some help from the great engineers of the past. The biggest cruise ship on the planet is almost complete. The Harmony of the Seas will be Royal Caribbean's 3rd Oasis-class ship. It eclipses every ship that came before it. Sitting as tall as Tower Bridge, it's as long as 5 jumbo jets and as wide as a soccer field.
When I really look at her, I'm amazed always, every single time by the size of the ship. It's big, but it's beautiful. It's awesome. You can definitely call this ship a small city. It can house almost 9,000 passengers and crew on board. It's a fully self-sufficient island, if you will.
The Harmony of the Seas is a miniature city, complete with theaters, restaurants, bars, and other attractions. How does such a gargantuan structure move across the open ocean?
The engines are the heart of the ship, and the electrical network is the veins to provide the power forward to the ship. Without the engine, the ship is not alive.
Building an engine powerful enough for this megaship would be impossible without help from one of history's great innovators. The Industrial Revolution gave birth to the steam-powered engine. It increased productivity, but enormous boilers were needed. To get rid of boilers, engineers broke the mold, burning fuel within a new engine. Compressing gasoline and air, and igniting it with a spark plug to drive a piston. The internal combustion engine was an industrial game changer. But as the 19th century drew to a close, an even greater innovation was just around the corner. Mechanical engineer Henrik Biergaard has come to Copenhagen in Denmark, a city which owes a debt of gratitude to an engineering marvel, which was inspired by a truly remarkable innovator, Rudolf Diesel.
This is the Oasis-class power station in Copenhagen. And inside, you'll find a giant version of Mr. Diesel's early engine concept, which changed the face of the industry globally.
When it first powered up in 1933, the diesel-powered HC Ørsted was the largest engine of its kind. It's 40 feet tall and weighs 1,400 tons. Back in the day, it could produce a mind-blowing 15 megawatts of power.
It's absolutely huge. Standing next to this 3-4-story tall engine is very impressive.
The real power of this engineering colossus comes from Rudolf Diesel's brilliant design, patented in 1894.
It's very hard to believe that the inspiration to this piece of engineering came from an object which actually fits into the palm of your hand.
The internal combustion engine had already made a huge global impact by the early 1900s, but Rudolf Diesel's design made it even more efficient. It doesn't need a spark plug, using only compression to ignite the fuel, thanks to a double-acting piston.
This is a fire piston, and this little piece of kit was what inspired Rudolf Diesel in his development of the diesel engine. And it works like this. You have a small cylinder where you add a bit of cotton wool. The cotton wool will work as fuel. You have a little piston. When you push down the piston here, the air will be compressed, the temperature will increase, and it will finally ignite the cotton wool. And it goes something like this. Compressing the air created heat. The heat forced the cotton wool to burn, turning it into energy, which forced the piston back up again.
The perpetual motion within the compression ignition engine works almost exactly the same way. Air is drawn into the piston and rapidly compressed, creating heat. High-energy diesel fuel is then added, causing combustion. This pushes the piston out to start the process all over again. Unlike spark ignition engines, the continual firing of the diesel-fueled piston creates superior power and efficiency.
This means that you're able to burn not only many different fuels, but also cheaper fuels compared to a spark plug engine concept.
This ingenious piece of engineering was supersized, creating the H.C. Ørsted engine. Incredibly, it still works more than 80 years after it was first fired up.
We're now about to ask Otto to start up the engine which was once the largest one in the world. Amazing. You can feel the vibration, and then you see slowly movement. Very, very impressive.
The H.C. Ørsted's 8 giant cylinders throw out more than 22,000 horsepower, operating at around 75% efficiency, compared to the 10% achieved by steam engines.
Basically, what you see here haven't changed dramatically in almost 100 years.
Diesel's innovation transformed the industrial world. Its unrivaled power and fuel efficiency made a huge impact on the world of shipping. The launch of the first diesel-powered liner in 1912 transformed the maritime world. Cleaner and more compact than its steam-driven predecessors, its engine was up to 3 times more efficient, increasing range and opening up new trade and travel possibilities.
I would say within mechanical engineering, it's the most important leap, no doubt of that.
The H.C. Ørsted may have been a monster in its day, but the harmony of the Seas engines are 6 times more powerful.
The total output of the ships is 93 megawatts. That equals the power of 1,200 road cars.
Fitting these massive engines inside the ship is an engineering feat in its own right. A team of nautical designers and engineers have set themselves an extraordinary challenge. Build the largest cruise ship in the world. The harmony of the seas dwarfs anything that came before it. When finished, it will be the largest passenger ship on the planet. The huge vessel is getting 6 Wärtsilä diesel engines, the largest of which is almost 43 feet long and weighs well over 200 tons. Fitting them into the ship was an engineering feat in its own right.
We are now on the main engine room of the ship, and we are going to test diesel number 1. So this baby here. This is one of the most exciting days of the project. Yo, Ivo, let's start her up. It feels great to see the engine alive. In total, we have 6 engines, and the total output of the ships is 93 megawatts. That equals the power of 1,200 road cars.
Without these supersized engines, the harmony of the seas won't make it out of the shipyard.
Starting of the main engine is one of the main milestones on the shipbuilding project.
The enormous size of the harmony of the seas is allowing its designers to do something truly remarkable. The ship has a split superstructure. That means there's a vast open space in the middle.
Now we are on deck 8, forward, facing backwards. We are on the Central Park area, one of my favorite places of the whole ship. The inside cabins are not anymore inside cabins, but we have a perfect view to the park. We will have solid pavement here, live planters, just like a normal park. This concept is totally unique. You cannot find it anywhere else. Only an Oasis-class has this split superstructure.
Its upper structure is impressive, but for the ship to be seaworthy, it has to deliver beneath the waves too.
So there are a few factors that are very important for the fuel efficiency of the ship. And clearly the biggest one is the hull shape. The hull shape needs to be extremely well designed so that you have a good hydrodynamic shape.
So how do you design the perfect hull shape for the largest passenger ship in the world? It would be impossible had it not been for an innovative breakthrough made over 150 years ago. Dr. Andrew Steele is in the British seaside town of Torquay, getting a taste of the power behind a perfectly designed ship hull.
This is a Phantom 19 offshore circuit racing class powerboat, and it's built for one thing: speed. The shape of the hull has been precisely matched to the power of the engine, and that means that this thing can cut through the water at incredible speeds, in excess of 100 kilometers an hour. This really is incredibly exciting. The ability of this boat to cut through the water would not be possible without the pioneering work of one man here in the seaside town of Torquay.
Over 200 years ago, engines were transforming the maritime world. But boat builders still had a lot to learn about ship design.
For centuries, shipbuilders had a kind of one-size-fits-all notion about ship hulls. There was one generic shape that was considered the most efficient, but there was no real way of testing this, of working out how much drag, how much resistance a hull would encounter as it moved through the water.
In 1870, engineer William Froude built a groundbreaking hydrodynamic testing facility.
It was here at his home in Torquay that Froude built the world's first tow tank.
Froude's 250-foot-long water tank allowed him to carry out precise tests at controlled speeds. He mounted handcrafted models on a carriage, then dragged them through the water on a steam-driven pulley.
Froude's original tank out there in the garden is sadly no longer in existence, but we do have this lovely swimming pool. And here we're going to try to explain Froude's revolutionary discovery and how it changed the world of shipping forever. We've got three different shaped hulls: a flat-faced square box, a slightly streamlined rubber duck, and then this sleek speedboat.
After making sure each object is equally weighted, Andrew tows the objects with a rope attached to a scale, measuring the amount of hydrodynamic drag.
You can see this isn't slicing through the water, it's sort of making a load of turbulence. If you look at the scales, 3, maybe even 4 kilos. That's a lot of drag, a lot of resistance.
Next up, a slightly more streamlined rubber duck.
Well, that feels much lighter, and the scales bear that out. Maybe 1.5, 2 kilos of force there. And you can see the pool much less disturbed. There are far fewer of those eddies. The duck's just skimming across the top of the water. But I still think we can do better. Let's try the powerboat. This is almost effortless, maybe 600 or 700 grams tops. You can see much less disturbance to the water. The pool's almost still. And even from this scale model, you can see why we make boats in this streamlined shape.
The key to Froude's discovery lies in a model's wake pattern.
Froude's real eureka moment was when he realized that he could use a law to relate the drag on a scale model of a boat to one that was full size.
Froude developed a formula, now known as the Froude number.
That Froude number can then be used to compare a model ship to a full-size one. By making sure they've got the same Froude number, you can work out how much drag the larger ship will experience, work out how big an engine you need to install, and it was this discovery that revolutionized hydrodynamics and the shipbuilding industry.
Froude's hydrodynamic testing facility hosted over 46,000 experiments. His work paved the way for the hundreds of state-of-the-art tanks in existence today, many of which have been christened with water from Froude's original tank. Engineers of the Harmony of the Seas are using huge 30-foot models to simulate a variety of sea conditions. The result, a super efficient bow design. A design that will be enhanced even further using a cutting-edge system known as air lubrication.
The air lubrication technology requires microbubbles, so we push the air through the bottom of the ship through a specifically designed grid that creates the microbubbles. We have them in a few locations on the ship in the forward part, and as the ship moves forward, the cushion of air moves along the ship's hull.
Microbubbles create an airstream under the ship. This cushioning effect significantly reduces friction and the amount of power needed to propel the ship. Air lubrication will increase the Harmony of the Seas efficiency by 5%. This colossal cruise ship may be streamlined underwater, but above, its sheer stature poses a huge challenge.
As we have such a big wind profile on the ship, it's almost like driving a skyscraper at the seas. We have to be able to control her.
Engineers will have to look to the innovators of the past for the solution. In a shipyard in France, the third addition to the largest class of cruise ships ever built is almost ready. The Harmony of the Seas is a record breaker.
It is 361 meters long, 47 meters wide on the waterline. We have over 2,700 passenger staterooms, and we can have almost 9,000 people on board at any given time. Largest cruise ship in the world, pretty impressive.
Designing a system that can control such a huge ship in unpredictable weather is a seemingly impossible challenge.
As we have such a big wind profile on the ship, it's almost like driving a skyscraper at the seas. We have to be able to control her to the direct position what we want to have to be.
Their solution can be found in an accidental discovery made nearly 180 years ago. Naval architect Lucy Collins is on the English coast, on a boat equipped with an innovation that dominated shipping in the 19th century.
And this is it, the paddle wheel. Once the steam engine came along, the paddle steamer was born, and it was unrivaled as the main form of ship propulsion across rivers and the seas.
By the 1800s, paddle-driven ships like the SS Savannah had the ability to cross the Atlantic, but it wasn't an efficient process.
So the paddles are on the side of the ship, and as it goes over waves, and particularly in rough weather, the paddles are going to start coming out of the water on either side, and this is going to reduce efficiency and speed.
Paddle steamers dominated the seas for decades, but engineers were looking for a viable alternative. Their inspiration came from an ancient invention.
For most of those early innovators, the focus of their attention was this, the Archimedes screw.
Dating back to the 3rd century BC, this crank-operated contraption was used to transfer low-lying water into irrigation ditches.
So we can see if we turn the drill on, we start to get water transferring up the pipe and then overspilling at the end of the pipe. So inventors realised that they could apply this to a ship. If you put the screw surface on the ship, it can push the ship through the water.
In 1836, engineer Francis Smith patented a revolving screw that could be used to power a 6-ton ship. But Smith accidentally snapped the 3-foot-long screw during testing, leading him to a surprising discovery. The shorter piece drastically increased the boat's speed. It was the precursor to the modern-day propeller. Even after his finding, the Navy believed that paddle power was the future.
Adamant about the advantages of his design, Smith decided he needed to prove his doubters wrong. He decided to pit his screw-driven SS Rattler ship against the paddle-driven SS Electro in a tug-of-war and a race.
Both ships weighed the same and had identical engines. Smith's lifelong work was on the line. Today, Lucy is recreating this famous event. She's taking on a propeller-powered bike in her paddle-powered vessel.
So the paddle wheel's got quite a good acceleration straight from the start. But it seems like the propeller blade is just reaching its full efficiency. And unfortunately, the paddle wheel just can't keep up. The paddle wheels are slipping, and it seems like the race is lost.
Smith's screw-driven vessel blew its paddle-powered opposition out of the water, ushering in a new chapter in propulsion.
That was the start of the propeller being the primary means of propulsion for ships from then until now, almost 180 years later.
In order to drive the largest cruise ship in the world, the propellers on the Harmony of the Seas need to be of epic proportions. Each of its 3 bronze propellers are 20 feet wide and weigh almost 45 tons. But the designers of this mega ship can't just make it go fast. They need it to have the ability to maneuver through small ports.
The ports we sail into are sometimes fairly small, so we have to really park it on a dime.
The Harmony of the Seas, the largest cruise ship in the world. 3 massive bronze propellers move this behemoth through the open seas quickly and efficiently. But this megaship can't just go fast. It has to be able to maneuver in and out of port.
The ports we sail into are sometimes fairly small, so we want to be sure that we can always maneuver the ship in a very safe way. So we're not dependent on tugs. We can independently maneuver the ship into the ports we want to sail into. We have to really park it on a dime.
Their solution lies with an invention developed in the 1950s by German engineer Joseph Becker. He designed something called the rudder propeller. His propeller could both move and steer the ship. It was revolutionary in its design. The modern incarnation of Becker's concept is being installed on the Harmony of the Seas. It's called a podded propulsion system.
We have 3 Azipods, each of them are 20 megawatts in size. And 20 megawatts you could translate to being about 200 family cars. It's a huge amount of power, but considering the size of the ship, it's what we need.
The 3 pods act like airplane propellers, pulling the ship through the water rather than pushing. Utilizing 5.5 kilowatt bow thrusters, they allow the captains unparalleled control. The pods can be turned in an instant, getting the vessel into locations that were previously off limits to megaships.
Well, the Azipods came as a result of really thinking outside of the box. It's ingenious.
As the Harmony of the Seas inaugural voyage draws closer, making sure the ride will be comfortable for all 6,000 passengers is a top priority.
clearest issue we have is that the ship is not stationary. It moves, it rolls, it heaves. There's all kinds of movements and acceleration on the ship, which makes it a little bit more complicated.
How do you keep such an immense vessel steady in even the roughest seas?
This is a gyroscope, and to explain how it works, we're going to need one of these.
A motorcycle's wheels do more than just power and steer it.
A gyroscope works by conservation of angular momentum, which means that when it's spinning around very, very quickly, it doesn't want to change the direction of that spin. And this can give some pretty counterintuitive effects.
These physical reactions can be extraordinary. An effect known as ghost riding sometimes occurs when a bike crashes and loses its rider, but then rights itself and continues its journey. This phenomenal sight comes down to gyroscopic forces acting on the bike as it tries to maintain its original orientation. So how does it work?
Well, I'm going to try and show you with this piece of apparatus here. What we've got is an ordinary bike wheel, but we've filled the inner tube with concrete just to make sure it's nice and heavy. So currently this thing isn't spinning, and that means it hasn't got any angular momentum. And that means it's pretty easy just to make it spin around. It's not very stable. However, if we get this electric drill, we can get the bike wheel spinning. And as we add more speed with the drill, we're increasing that angular momentum. Now it's moving very fast, and now if I give it a whack, you can see this thing is stabilized.
And that's why, in extreme circumstances, a wheel can refuse to lie down. It's the stabilizing effect of a gyroscope that maritime engineers are interested in.
If I get it spinning nice and quickly, I can just balance the spinning wheel on my hand.
Gyroscopes can do this for a ship. In 1917, American inventor Elmer Sperry took advantage of gyroscopic forces for the first time in a large vessel. He equipped the USS Henderson with 2 enormous gyro wheels. Each wheel weighed 60 tons. Inside, 10-foot flywheels spun at an incredible 1,100 revs per minute, creating huge amounts of angular momentum in order to minimize the ship's roll. It was a huge engineering breakthrough, but his brute force approach was impractical. As technology has developed, so has the use of gyroscopes.
Over the years, pioneering scientists and engineers have experimented with these gyroscopic forces to the point where nowadays we can fit tiny gyroscopes on the surface of a computer chip like this one. And they're used everywhere, from mobile phones to aircraft and even ships.
The harmony of the seas takes the magic of the gyroscope into the 21st century. Instead of using giant spinning wheels like those employed on the USS Henderson, the harmony of the seas uses a small gyroscope as a sensor, which controls mechanical stabilizers via computer.
So in rough seas, what we can use to minimize the roll and the movements of the ship are stabilizer fins. And they are actually fins that emerge laterally from the ship's hull. This is the location we are in now. And what it does, it's sort of like a wing that comes out of the ship. It emerges laterally like this, and then it turns around its axis.
A stabilizer blade is recessed into each side of the ship. They're deployed when seas get rough.
Stabilizer mostly counteracts the roll, so the sideways movement of the ship. So if the gyroscopes feel that the ship starts moving this way, it asks the fin to exert force so that it counteracts the movement here, so it tries to always right the ship.
It's been a century since the first cruise ship set sail on the world's oceans. Now, by drawing on the innovators of the past,
Standing next to this 3-4-story tall engine is very impressive.
adapting their ideas, honing them, and making trailblazing innovations of their own. The engineers, designers, and workers constructing the harmony of the seas